minus 20, still counting at this time. We have ignition sequence start. 6, 5, 4, 3, 2, 1, 0.
Roll program started. Our vehicle going now to an azimuth heading of 72 degrees. All 5 F1 engines started.
Good afternoon, and welcome to the ATCO SpaceLab Speaker Series. My name is Alicia Tropak, and I am the Director of Transformation at ATCO, and I will be your moderator today. I would like to begin by acknowledging the traditional territories and original caretakers of the land where we make our living and enjoy its abundance with our friends and family. I am honored to live and work in Treaty 7, the traditional territories of the Blackfoot Confederacy, Niitsitabi, comprised of Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley nations. The city of Calgary, Mohkinstsis, is also home to the Métis Nation, Region 3. I would also like to pay my respects to elders past and present in the communities and regions where we operate. This is the 6th lecture of the ATCO SpaceLab Speaker Series this year. These lectures are a chance for us to share knowledge and insights from thought leaders, providing our ATCO colleagues and ATCO's network of peers, partners, and friends with the information on promising developments, trends, and leadership in exciting and relevant fields. We previously heard from Dr. Misha Kirchhoff from the University of Arizona on November 7th. In case you missed it, please visit ATCO's YouTube channel for a recording of this lecture. This is the final lecture for 2022, and we'll be announcing new lectures next year. Before we get underway, I would also like to remind you that this is a one-way video and audio format. Please ask questions by using the question icon on the right of your screen. We will open up the question functionality about halfway through Professor Bradley's lecture. Now, I would like to introduce Andrea Kleber-Langen, Vice President of Transformation at ATCO, who has some welcoming remarks and will introduce our speaker.
Thank you, Alicia. Before I get started with introducing our wonderful speaker for the day, I want to reflect on my role in reconciliation as well. I recognize the various traditional, unceded, and ancestral lands on which we work and serve our customers, lands that I live on and work and enjoy my life today in, and offer each of us the opportunity to do the same, regardless of where you are, no matter where you are joining us from today. I reaffirm my commitment and responsibility in improving relationships between nations and improving my own understanding of Indigenous peoples and their cultures. Thank you all so much for joining us today, the final ATCO SpaceLab Speaker Series for 2022. This year, we've had the opportunity to learn about wind energy, robot locomotion, the dynamics of river ice, innovations in continuing care for elderly people, and applying artificial intelligence to complex problems in the quantitative sciences. In addition to presenting this speaker series, ATCO's transformation team also leads ATCO SpaceLab. SpaceLab is an enterprise-wide framework of support for any of our ATCO colleagues who are interested in exploring and testing sustainable new value for ATCO. SpaceLab can provide funding, it's a source of expertise and other support, and this team, this wonderful transformation team, has supported the achievements of over 110 projects since the fall of 2019. Today, we're joined by Professor Elizabeth Bradley, who will tell us about her work in the field of chaotic dynamics. Professor Bradley, we are looking forward to finding out about the mathematical and computational techniques used in chaotic dynamics and how you apply them in interesting examples ranging from science, engineering, and I understand even dance. We're excited to hear more about chaotic dynamics today, and we recognize that this study is relevant to ATCO in a number of areas. ATCO and our customers. Areas such as the diffusion dynamics involved in mixing gases and pipelines, as is the case with hydrogen blending, in power grid loading and control mechanisms, and in weather prediction, one of our often revisited topics. Dr. Bradley received her PhD from MIT and has been a faculty member of the Department of Computer Science at the University of Colorado since 1993. She's an external member of the Santa Fe Institute and the recipient of the National Young Investigator Award, Packard and Radcliffe Fellowships, and the University of Colorado System's highest teaching award. It is my pleasure to welcome you, Dr. Bradley. We're absolutely delighted you're here to be with us today, and we look forward to learning from you.
You're live, Professor Bradley.
Okay, great. Thank you so much for the introduction and for the invitation. Listening to you outline the speaker series and this that you've put together made me want to close my computer and go listen to them. I hope that I can contribute something to that. I'm interested in analysis, modeling, and sometimes control of nonlinear dynamical systems, and that's a mouthful. It's way too much to work on, let alone to talk about, so I'm going to cherry pick. And you'll notice, by the way, I changed my title to something slightly different than what was advertised and slightly less enigmatic. I have to offer an apology before I get going. My cat has a habit of launching himself onto the back of my chair while I'm lecturing, so please don't be surprised if you see me duck. It really amused my students while we were teaching by Zoom over the pandemic. So, nonlinear dynamics. I'm going to start with a whirlwind introduction to this field, then give you a bunch of examples, and I'm going to pull in some fun math along the way. Now, depending on your training, nonlinear dynamics may not sound very interesting to you, but you've probably heard of chaos theory. So chaos theory, and this is not chaos in your living room or chaos in the Middle East. It's a word that was co-opted by mathematicians in the 70s to describe a different kind of thing. Behavior in a dynamical system that is highly sensitive to initial conditions, small taps, but that has some structure. So let me unpack that. Dynamical system, a system that changes with time. It evolves in some way with time. That's the kind of thing I'm interested in generally. A dynamical system that is exquisitely sensitive to small changes is reacting to what are called its sensitive dependence on initial conditions. But even though the system is exquisitely sensitive, like actually mixing in pipes is certainly like this, the weather is certainly like this, and I'll try to tie some of my concepts back to that. There is, if you know how to look at it, there is an overall structure. So you may have heard one of the metaphors we use in my field is the butterfly effect. So a butterfly flapping its wings off Tokyo sets off a hurricane next week in the Aleutians. Apocryphal, but it actually gets the point across that a small change can be amplified by the system's natural dynamics into some downstream effect far away in space and time that's pretty big, even though the initial perturbation was small. Another metaphor that we use in my field is an eddy in a stream. So if you looked at an eddy in a stream, you would see that there's, it's kind of the same shape and the same size. And if you looked at a particular patch of it, the water would be flowing mostly in the same direction. But imagine a thought experiment. You drop a wood chip in that eddy, and then you do a time-lapse photograph from above, and you watch the path that wood chip traces through the eddy. It would be very complicated, but it would stay on that eddy. Now imagine dropping another wood chip, maybe an angstrom to the left, and doing the same experiment. That wood chip would travel along the same path that the original one did, but eventually it would get a little separated, and then it would take a very different path, but again, through the same eddy. That's what I mean by the tandem of sensitivity and structure. Here's a chaotic system that I built. It is a double pendulum. I apologize, I didn't have a tripod when I made this video back in grad school. 2 pieces of aluminum and 4 ball bearings. So extremely simple physics, but extremely complicated behavior. And that's one of the really cool things that gets people interested in chaos alongside this business of sensitivity and structure. So structure. If, again, you know the right way of looking at this, you can see that structure. And I'll get back to that in a minute. But first, when we all take physics, if we take physics, we learn how to write down equations for this kind of thing. And they involve things like force balances and torque balances and M and G and sine theta, things like that. And I would point out to you that those equations do not have random variables in them. That is, got nothing to pick up here. If I drop this tissue box, there's not a small chance that it's going to go up and a large chance that it's going to go down. If I drop it, it's going to go down. So the current state of the system determines the future evolution. It is a deterministic system. Cause and effect are linked. But chaotic systems are, in practice, like the weather, unpredictable. So why? Because that sensitivity, the fact that if you tap them just a tiny little bit, that can make a huge difference. That sensitivity can amplify microscale effects that we don't think about or can't measure, like an air molecule bonking into my pendulum, into macroscopic effects that we do see. So even though the system is deterministic, the behavior can be unpredictable. And there's all sorts of existential weirdnesses about chaos, which make this a really fun field, and that's one of them. Where does that sensitivity come from? Loosely speaking, nonlinearity. Nonlinearity, and that's an important concept. We all are quite familiar with this. The thing that happens very commonly in everyday life is, imagine like my car, I fill it up with gas, I drive 200 kilometers and the gas gauge barely moves. And then I drive another 200 kilometers and the gas gauge plummets. So what I want is a linear relationship between the level of gas in the car and the needle. I want it to look like this. But what it does is bang, like that. So it's a nonlinear relationship. We also experience this with our cell phones. Okay, you charge one of these things, you keep it in your pocket for a day and the charge goes down by 5%. But once that charge is down to 30%, especially if you're in an airport when you really need the thing, the remaining charge just plummets. Again, a non-linear effect. Given that the universe, not just cell phones and gas gauge, but the universe is largely non-linear, we need to care about this kind of thing. So nonlinearity, deterministic, nonlinear, dynamical system evolution. Okay, so back to that business about knowing the right way to look at these systems in order to see the tandem of structure and sensitivity. That goes to a representation that we use in the field. It's called the state space. Many of you, I'm sure, have had contact with this. It is the space whose axes are the state variables of the system. Excuse me. The state variables are the variables whose values tell you where the system is, what the state of the system is. And that's kind of circular and tautological, but let me actually give you, unpack that a little bit. So imagine, you know, the new movie, the new Avatar movie is coming out in a couple weeks. They did a tremendous amount of motion capture for that. They were capturing the dynamics of moving bodies. And imagine the state variables of the human body. So imagine the elbow, okay? How many variables do you need to describe the elbow? Well, you need an angle and you need an angular velocity. Okay, those are the two numbers that you need in order to fully specify the state of an elbow, a functional, healthy elbow. It's not clear why you don't need acceleration too, but we can talk about that in the Q&A. Wrist. You need not one angle, but two angles. So there's that angle and there's this angle. And you need the corresponding angular velocities. So 4 numbers, 4 state variables. The state space will have 4 axes, which gets hard to visualize. The shoulder is even more complicated. You've got this angle and this angle and this angle. So 3 angles to describe the state of a shoulder and 3 angular velocities. So a 6-dimensional state space. And a body moving through space, rather, let me start this over. An initial condition, a state of the body, is going to be a point in that very high dimensional state space. And as the body moves, or the dynamical system evolves, that it's going to trace a path through the state space according to the movement of all the pieces. So an initial condition, a trajectory from that initial condition, and then maybe there's some asymptotic behavior. So imagine a pendulum, and pull it like this, it's going to swing down, and eventually it's going to end up like this, hanging straight down. That's what's called an attractor. An attractor. It's what's left after a transient dies out. That many of our definitions are circular. I apologize. Let's see. There are, and let me back up a sec again. In physics, when you learn to look at dynamical systems, you make plots of things like position versus time and velocity versus time. That's very different than what we do in my field. We plot velocity versus position, which is kind of weird. The reason we do that is because the state space, that representation, suppresses temporal detail and brings out patterns in the relationship between the state variables, loosely speaking. Anyway, so that pendulum swinging down like that, if you plot it in the time domain, it would look like this. What does it look like in the state space? Something like that. There is a trajectory from this initial condition that kind of spirals into that attracting fixed point, perhaps at the origin of the state space. That's one kind of an attractor. Here's another, a periodic orbit. It's not a fixed thing, but it repeats. Here's the power cord from my computer. What's in here is a sine wave, 60 hertz, 110 volts. The power system that feeds the outlet into which this is plugged is a dynamical system that is designed to have an attractor that looks like that, is a periodic thing. If you looked at it in the state space, it's a circle. What comes out the other side here, by the way, this is the 110 volt. Out of this transformer comes a fixed point, fixed 12 volts or whatever. So those are two kinds of attractors. They're okay, fine, but the really interesting ones are chaotic attractors. And this is an example of a canonical, famous chaotic attractor due to Edward Lorenz, who was interested in prediction of weather and wrote a famous paper back in early 1960s about this. And as you can see, the trajectory is not ever dying out to a fixed point, and it's certainly not repeating. It's relaxing indeed to an attractor, but that attractor has all sorts of really cool properties. They are often fractal. That's a common misconception in the popular science press, that chaos and fractals are the same thing. It's not true. There's not an if and only if. It's not even an if. There are fractals that have nothing to do with chaos, and there's at least some chaotic systems that don't have fractal state space structure. So don't conflate those two. That second bullet on my slide is that business about sensitive dependence on initial conditions. And the last word in that bullet is how sensitive they are. Any small change grows exponentially. The third bullet is something that is useful for the purposes of control theory. It says that if you are standing on a point on a chaotic attractor and you draw a ball of radius epsilon around your feet, this property allows you to assert that a trajectory on that attractor will eventually get within that ball. So it'll eventually get near you. And that's useful. I'll tell you in a minute how one way that can be useful. And there are tons of other interesting features that, you can make a course about this, and I have. So the universe is, again, largely nonlinear. It's been famously said that the study of non-linear systems is like the study of non-elephant animals, and that gets the point across. It's not all chaos all the time. For example, a healthy brain, if you look at the EEG, it is chaotic. Certain recreational drugs make your brain go more periodic. A normal heart is largely periodic, the normal sinus rhythm. It's not quite periodic because there's beat-to-beat interval issues. But the heart can undergo what's called a bifurcation and change its behavior, go into something called ventricular fibrillation, which is chaotic, and it kills you. It's well known that there's chaos in population dynamics, and there's tons of chaos in the universe writ large. Pluto's orbit is chaotic. Mars's obliquity is chaotic. It's all around us. It's really cool. So we need to know about this. It's not an academic thing at all. And importantly, it turns up in flows of things. Weather, probably in your pipe flows that you mentioned. There's one of my colleagues in the civil engineering department who has worked on the fact that Marine invertebrates actually use chaotic mixing. They use chaos to get the eggs and the sperm to get together in the water around themselves. So lots of fun things. If you want to know more about this, any of this, I teach a MOOC, Massive Open Online Course on it, and that's the t-shirt that I'm wearing. It's under the Complexity Explorer website from the Santa Fe Institute, and you can get to it from my webpage. That slide says 2015, but it's given every year. Okay, so nonlinear and chaotic systems have all sorts of cool properties. I'm interested in how to turn them to advantage. And the cartoon version of that is, where do we release the butterflies to steer the hurricanes or break them up? Florida would like that right now, right? This is not going to happen for a variety of complicated technical reasons. There's no way this is ever going to happen, but there are some opportunities. And I'll talk just about a few. So imagine, from a control theory standpoint, your task is to get to some point in state space. There's some starting point A, and you need to get to some state space point B. Maybe it's stabilizing an inverted pendulum. I don't know. It's some point in state space. And traditional control theory, you figure out some path that maximizes or minimizes some cost functional, and you use your controller and so on and so forth. And here's another idea, which is, if there is some way to diddle your system with some knob such that it travels on a trajectory that goes to a chaotic attractor that at least gets close to the point you want to get to, then you're done. You just turn the knob to that setting and you sit back and you wait. And the system will get there all on its own. And that's nice, but if you remember, when I gave you that definition of reachability and denseness back in the other slide, I said if you draw a ball around your feet, the trajectory will eventually get into that ball. So there's still an eventually hanging around out here, and there's no way to prove anything about it in closed form, and that can be a problem. So denseness gives you reachability, but it can take a long time. All right, so can we leverage some of the other properties of chaos to get around that? That is, can we figure how to tap the system ever so slightly at exactly the right time to get to that red X faster? And the answer is yes, but the problem is that finding the tap is hard. Another problem is, imagine if you tap it just a little bit wrong. If you mess up, your error is going to blow up exponentially, and that's bad. Okay. So power grids, you guys mentioned power grids, are nonlinear dynamical systems. They're spatiotemporally extended, which is even more complicated than anything that I've done a whole lot of work on. And their dynamics depends on, among other things, the inertia in the generators. Again, I'm sure that this audience knows more about this than I do. And that inertia plays a stabilizing role. But renewable sources don't have as much or any inertia, and it can really matter where those renewables are in the network. That is how the inertia is distributed in the network. You can see my cartoons. So my student Sam Molnar did some work on this. She's now with the National Renewable Energy Lab in Boulder doing a little bit more on it. So it turns out that, nonlinear dynamics can help you with that kind of analysis. Another thing that I've been playing with actually fairly recently is extracting the scaling region of a curve. So given a plot like the top one in my slide, is there a scaling region? Now a scaling region is, this sounds really simple, it's a diagonal line, okay? Simple, right? Easy. It's not, because the curve might actually bend a little bit and you might not see it, or you might really want to find a nice diagonal line. So you might, in a subjective task like this that's subject to confirmation bias, this can be problematic. So we figured out a way to make that a little bit less subjective, which is nice. And there's lots of other things going on in my group. I have a group of fabulous students over the years, just wonderful people. And I'd like to spend a few minutes on two applications from this group that have to do with computers, okay? Computers. And the first one is, could computers themselves be chaotic? So could a computer, could this thing that I'm using to give the talk, and could this thing that you're using to hear this talk, could it be acting chaotic inside its little metal box? So here's a performance trace that tracks some memory use metric during the evolution of the execution of that simple microkernel that's at the bottom of the slide, which those of you who do programming are trying to figure out what the heck's going on. This microkernel, 3 lines of code, is initializing a matrix, a 256 by 256 matrix. It's initializing it in column major order. So it's doing this stripe and then this stripe and then this stripe. And we call this repeatedly, use the hardware performance monitor registers in the chip, gather them, and that's how we got that trace. And if you look at that trace, if you squint, you can see that there's a pattern, but it doesn't quite repeat. And after listening to me talk about this stuff for 10 or 15 minutes, I hope that that makes you kind of smell that that might be chaotic. A pattern, but it doesn't quite repeat. Okay, very simple program. What does a performance trace look like for a more realistic piece of code? This is a trace from one of the spec benchmarks. It's, I think it's gzip, I can't remember. No, it's bzip. Again, clearly some structure here, but it's complicated. So how to model and analyze this behavior? Well, most of the people who design and analyze these kinds of things treat their behavior as stationary stochastic processes and use metrics like floating point operations per second, flops, or maybe they go so far as using means and variances. And I would submit to you, if you look at that trace, approximating it using its mean and variance is pretty clearly a violent simplification. It actually amounts to an assumption that the process involved is linear and time invariant, and computers are not time invariant. They're certainly not linear. Think about what a transistor does. It's a switch. There's some sort of transfer function like that. That is not a line. It is not a line. And I would claim computers are not stochastic. They are electrons running around in silicon and metal. They are deterministic, nonlinear dynamical systems. So how about using techniques from nonlinear dynamics to analyze them? Plotting attractors and calculating, fractal dimensions and things like that. All well and good, but there's a problem. How can we do that if we can't measure the internal state variables of the system? They're inside this metal box. This is one of control theory's other big problems. It's called the observer problem. If you have a black box and you can measure its output, what can you deduce about what's inside the box? So remarkably, dynamical systems theory provides a way around this. Not perfect, but it's really good. It's called delay coordinate embedding or delay reconstruction, and it works like this. You take your data, you stick your sensor in the side of the black box. You measure one variable, so a scalar time series. There's some conditions, but we can talk about that offline. And then you plot it against delayed versions of itself. That is, you plot exit time t on the horizontal axis, exit time t plus tau on the vertical one, and so on and so forth. So as an example, there's a data set that I've concocted for this example. And let's say I choose to use 3 axes for this. That's called the embedding dimension. It's key. And I choose to use a delay of 0.2 seconds. Those choices are not easy, but again, we can talk about that offline. So the coordinate of the first point in this space, you'd look at this value of x, sorry, the 1 point, I don't know if you can see my cursor, but I'll just narrate it. The value of x at time 0.1 is 1.3. That would be the coordinate on the horizontal axis. Then you move down 0.2 of a second to the x equals 1.0. That's the third line. That would be the coordinate on the vertical axis. And then the coordinate on the axis that comes out of the screen is 1.1, which is 0.2 of a second later. As you can see, I think of this as kind of using a comb, and you slide a comb through your data. The number of teeth in the comb is how many embedding dimensions you're using, maybe 1, 2, 3, 4. The spacing between the comb teeth is the delay. So this is delay reconstruction. To get the next point in the reconstructed trajectory, you just slide the comb down. And if you do that and do it right, there's some caveats there, you're guaranteed to get something that has the same topology as whatever was inside the black box that you sampled with that single sensor. Now, topology. Topology, this will come back in about 5 minutes. Topology is the fundamental mathematics of shape. Our eyes react to geometry, not topology. So what you get by doing this doesn't look right to us, but it is, there's a really important implication of having the same topology. So there's this thing on the right in the black box that looks like a mask with 2 eyes in it. I can't measure it, but I stick one sensor in there. I measure one of its state variables, for example, and I do this delay reconstruction stuff that I had on the last slide. And I get that thing on the right, on the left rather, that looks kind of like a pinwheel. And again, they don't look the same to us, but there is a mathematical assurance that they are related by a particular kind of function called a diffeomorphism. And what that gives us, if all of this doesn't make any sense at all, is that there are things that we care about in dynamical systems. They're called invariants, and many of them are invariant under those kinds of transformations. And all of that is to say that, again, you've got this thing in the black box that you want to know some features of, but you can't measure it. So you can measure one piece of it, you do this reconstruction, and the theorem tells you that you can do that same calculation on the reconstructed thing and get the result that you would have gotten if you could have observed the whole thing. So this feels like magic when you first see it, but it really works. And there are some conditions on the theorem, of course, they're not onerous. But there are practical constraints on implementing this in floating point arithmetic on finite amounts of noisy data, which are what really end up biting you in painful places. I can explain that offline as well. So going back to where I started, which was this performance trace at the top left. If I go through that embedding procedure on that data, I get that thing on the top right, and I do my calculations of my favorite dynamical invariant. I happen to do the Lyapunov exponent here, and I find that the dynamics are indeed chaotic. Okay, the dynamics of a computer, probably the one I'm running on right now, it is being chaotic. Not the result that it is producing, thankfully, but the way that it is using its memory, the way that it is using its processor changes chaotically from time to time and from run to run. So that's a little bit scary, but not too bad if you know about chaos. What happens if we use a different machine? If you run the same code, so this is one piece of code on an Intel Core 2, this is the same code under the same initial experimental conditions with the same measurement infrastructure on a different x86 based machine, you get very different dynamics. Here, that machine, that computer, it's chaotic. Here, it's periodic, okay? And what this says is actually not surprising if you think about it a bit. The implementation of the hardware plays a role in the performance dynamics. And this makes total sense, or Intel wouldn't work to design new chips. So in retrospect, it makes total sense. Software also affects performance dynamics. This isn't surprising, I guess, because or else we wouldn't work so hard writing code or compilers. What's going on here? It's the same computer as here, but a different way the matrix is being initialized. Okay, so we can do this kind of reconstruction and reconstruct the attractor for the dynamical system, not perfectly, but up to diffeomorphism. And that is that's neat, but it is actually useful as well. So this is one of these standard kinds of things that people do when they're predicting, when they're building prediction models. They take a time series and they take the first 90% of it, they use it to build some sort of a model, and they use that model to predict the last 10%. And I'm showing you here the last 10%. The model that was used, not a machine learning model, the model that was built for the prediction was one of these things on the top right. and then the prediction algorithm was basically nearest neighbor prediction, or k nearest neighbor prediction. Wherever it went the last time it was near here is where it's going to go the next time it's near here. That's nearest neighbor prediction. And it works pretty well. The little red circles are the prediction, and the blue X's are what it should have predicted, and you can see it's pretty close. So why could this be useful? Imagine if this is a prediction of the instructions per cycle in a running program, and you could predict half a second out that the code that you're running could only take advantage of 2 of the 7 cores on your chip. Well, you could power down the other 5 because you're not going to need them and save some power. So that's the first of my 2 computer examples. The second one is a different consideration. And where this comes from is that the computer that I'm using to give this talk is also my laboratory. And the reason for that is that if there is a chaotic system, it's ordinary that the equations that model its evolution cannot be solved in closed form. That is, you cannot write down a solution, x of t equals blah, 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 and ever stop. And that's, you can see there's an if and only if arrow up on my slide there. That's an important thing. So chaotic systems cannot be solved in closed form. So you have to solve them numerically. And what that means is you have an initial condition for the system at some point in state space. You have the differential equation, and then you wrap that all in some algorithm that says, given this differential equation, where will that go next? Where next could be a 10th of a second later, or a 20th of a second later, or a 100th of a second, whatever. So that's pretty onerous, and it's good we have computers to do that, but we didn't always have digital computers to do that. And it has been the case that we've needed to solve differential equations for some time now. Back in the middle of the last century, there were some differential equations that the Army needed to solve. All the armies needed to solve. It had to do with, shooting things and blowing things up. And these were all equations that needed to be solved and couldn't be solved with in closed form. So someone, some device, some sort of computer had to do that point by point, highly onerous, kind of step by step, saying, where is this thing going to go next? Those of you who've taken these courses, this is, like Runge-Kutta or Adams or Moulton or Bashforth or Gear or whatever. There's like legions of names for algorithms that do this. And these poor souls were sitting at these desks 40 hours a week doing that with paper and pencil. I would kill myself, I think. So these actually, there's another interesting piece of history here. If you look at that slide carefully, you'll see that every single one of these people is female. And indeed, they were called computers. They were things that computed, people that computed. And so I would point out to you that the first computers were all women. Now, if you are, if your computer is your laboratory tool, you better be able to trust it. And there are legions of problems that can arise in solving differential equations. And if you remember nothing else from this talk, probably this is the single most useful thing to remember. What I'm showing you here is a bad scan, my apologies, of a page from a paper by Edward Lorenz, where he's showing you that depending on the time step that you give your method, that is, I know the system is here at this time, and you ask the solver to say where it is 1/10 of a second later. Depending on that time step, you might get different behavior. So this picture is the same dynamical system, the same computer, the same solver algorithm, but different time steps. And the dynamics are completely different. And this shouldn't be. This is actually actually not slightly, it's very terrifying. This would be like you pointed the Hubble Space Telescope at a nebula and it transformed that nebula into a quasar. These are different kinds of dynamics that can turn up in dynamical systems, and your observing instrument, your computer solving the equation, has turned one into the other. Okay, so the time step can change the results, and the time step shouldn't change the results, we hope. Computer arithmetic can also change the results. Here, this is work by another one of my PhD students. She was on the left is a simulation of some dynamical system, it doesn't matter which one, using single precision arithmetic. On the right is the same system, same computer, same solver, everything, same time step, different arithmetic, double precision arithmetic. And neither one of them is right, but the one on the right is more closer to right. So floating point, the arithmetic, the precision of the arithmetic can affect things. And precision of arithmetic, you read about like a 64-bit computer, a 32-bit computer, or so on and so forth. Those numbers have to do with the grain size of the numbers that the computer is good at working with. And if you get down close to the grain size of the number, the smallest number the computer can represent, you're in deep doo-doo. All right, this is the really fun one. This is a simulation of the planets in the outer solar system done before Pluto was demoted, obviously, because it's still in there. And it's done with a solver, a simulator that is a really high octane one that the celestial mechanics people use. If you use a slightly less good solver, you can see the planets start to oscillate. And if you use a first page of the textbook kind of solver, Jupiter gets ejected. And probably people are smiling or laughing, but again, this is really kind of scary because this kind of thing, planets can get ejected, especially big, heavy ones close to their star. Planets can get kind of messed with if another star goes flying by. So the observing instrument has changed the behavior in a way that, you know, is dynamically potentially meaningful. So this is the moral of this piece of the talk is your results may contain spurious dynamics that look exactly like what the physical systems do. So what should you do? Well, I just showed you some things that probably made you think of exactly the right things, which is it's very easy to change the time step. Okay, it's very easy nowadays to change the method. Like MATLAB has ODE 23 and it has ODE 34 and it has ODE 43. Just use a different one and see if your results change. If they do, you should worry. If they don't, that's not a proof. Okay, it should simply increase your confidence. It is not a proof that you're right because there could be some other effect that's biting you. Change the arithmetic. That's a little bit harder because you have to change all your floats to doubles and things like that. But it's important. And my red text on the slide goes back to that notion of the fact that a computer does not work with real numbers. It works with quantized numbers, floating point arithmetic. There is the machine epsilon is a code word for the smallest number that a computer can represent. And you can imagine that if you changed the time step down to some number that was close to machine epsilon, things would go kablooey, not for a dynamical reason, not because of the solver, just because of the computer. So be a little bit careful. Okay, how are we doing on time? Here's another nonlinear time series analysis application. Paleo records. When you drill a core into a glacier or an ice sheet, you're pulling up a record of the conditions on Earth at the time the snow fell that turned into the ice at that depth of the core. This particular core from West Antarctica is 3.3 kilometers long, and it covers 67,000 years of Earth's history, sampled at a ½ centimeter spacing. So it is a time series. Maybe we could get some traction on this with the methods of nonlinear dynamics, just like the time series from the computer. So in 1984, a paper came out in Nature claiming that at least one such record did support that kind of analysis, and that the results indicated that there was a climate attractor. 2 years later, Peter Grasberger took a shotgun to that idea, and he showed that the record did not have enough data to support the conclusion drawn by the previous paper. Now, Peter is one of the originators of the technique that was used in that previous paper to make the claim, so this was a big ouch. What was that mathematics? Both of those papers used that delay reconstruction technique to reinflate the attractor, and then they calculated something called the correlation dimension, which involved doing some calculations and then looking for a scaling region in the curves that come out of it. Scaling region, you saw that before. So that's something I just did in a little bit of a drive-by. Then you fit the slope of those scaling regions with some sort of a line, and that gives you the correlation dimension. And what you should do is repeat that for 1 embedding dimension, 2 embedding dimensions, 3 embedding dimensions, 4 embedding dimensions, and make sure that as you increase the embedding dimension, the results stabilize. And they didn't for this data set. So there wasn't enough data. So we thought, well, hey, we got better data. Maybe we can try again. And it still didn't work. Basically, we were able to do these calculations, but if you look at the M values, that's the embedding dimension, you see that the dimension, the D sub core, is not converging. So, and we couldn't go above M equals 10 because we knew we didn't have enough data to support that. So basically, there's still not enough data, and the meta point here is this is the Achilles heel of nonlinear time series analysis. You need a ton of good data to get it to work. So what can we do? This is where we're detouring off away from nonlinear dynamics and into information theory. And this goes back to Claude Shannon. Many of you may have heard of him. Shannon produced many, many amazing things, but one of his most amazing things was the concept of entropy, calculated from a sequence of symbols to talk about predictability. So imagine you have a fair coin, heads and tails, and you flip it, you get a head, and then you flip it again, it should be equally probable that you get a head or a tails next. If you had a biased coin that you flipped it, and every time you flipped it, it came up heads, then that would be completely predictable. You could have a slightly biased coin that was 25% heads, 75% tails. And we've all probably done these calculations in statistics classes where you kind of calculate those percentages and then you bin them and then you do a p log p and you get some sort of a prediction scale. Normally this is calculated Shannon entropy as defined on symbols like heads or tails. And there's a way was developed, I don't know, 15 years ago to do that on continuous valued data. It's called permutation entropy, and it's really powerful. It might be something that could be used in some of your applications. I don't know. But it's, instead of symbolizing the data into bins, it symbolizes the data into whether or not it went up or down between successive time steps. And again, I can point you to papers that give you short explanations of this. But I'll just tell one story about this, which is I went to a colleague of mine who works on ice cores, and he gave me, the data set, this data set, and we did this calculation on it, and we got this answer. And I took it to him and I said, what happened 6,000 years ago? Because there's this great big bump in the data. And he turned to the postdoc and he said, Tyler, wasn't that the chunk of core that you analyzed with the old machine? So yes, the old machine had caused problems. It had introduced noise into the data, which made it less predictable. And less predictable is higher up in permutation entropy. And the noise that it introduced was on such a small scale that they didn't see it when they were just kind of scanning the data. You had to go back, you had to know where to look to see this manipulation, this anomaly. So we used this plot to get some money from the National Science Foundation to go back and resample that chunk of core using the new machine. And that removed the nasty bump in the deuterium data, which confirmed that the old instrument had indeed been the culprit. So this information theoretic technique flags other anomalies in the data as well. This thing, again, I don't know if you can see my cursor, but there's some spikes at 57,000 years ago. That was because they dropped 110 centimeters of ice on the floor, and so it got all mixed up. There's some other spikes like at 30,000 and 25,000 that are due to different anomalies. And basically the point here is that this technique flags obvious anomalies that are not obvious to the eye, and so it's useful. It's now part of the analysis pipeline in the isotope lab that gathered this. So flagging anomalies is fun, but doing science is even more fun. And we were able to show some new scientific ideas from the permutation entropy calculated on this ice core, which was kind of fun. So that was that. And, you know, again, I said I'm cherry picking. There's papers on each of these that are on my webpage if you're interested. And I hope by now you have gotten the picture that I'm interested in just about everything, and it gets worse. Back to that notion of topology, the fundamental mathematics of shape. People have probably seen this kind of picture. The topology of an object is so abstract, it doesn't, there's no measuring involved. The topology of an object tells you how many pieces it has, how many holes it has, how many voids it has. So the two objects on the top here, the coffee mug and the donut, are identical from the standpoint of topology. They both have one piece and one hole. The two objects on the bottom have largely similar geometry, the same shape to our eyes, but one of them has a bunch of holes and the other doesn't have any. So very different topology. And this can be surprisingly useful in the analysis of data. Again, there may be some applications here in your world. But the problem is that computing the topology of an object when you don't have the whole object, you don't have the whole donut, you just have some samples of it. How do you do that? Well, one way to do that is to inject a bit of geometry back into the process. You have these points on the left-hand image that are samples of an object. Well, if there's samples of an object, there's probably pieces of the object, or how do I say this? There's probably other chunks of the object nearby. So why don't we take each point and make it into a ball? And why don't we then take the union of those balls and look at the shape of that thing? And let's repeat all of that by and change the shape of the balls and repeat all of that. And so what I'm going to do is play you a movie where each of those points in the left-hand thing are going to get enlarged into balls, and you'll be able to see how many pieces and how many holes the object has as those ball sizes change. So watch for holes first. See some little holes form, and there's a little hole, and there's a slightly bigger hole, and then it goes away, and now there's one big hole, and that hole lives for a long time. But eventually, when the balls get really big, that hole goes away, pop, too. So at the beginning, and this movie will loop, the object has lots of pieces and no holes, and then it starts to, the pieces start to merge, the holes start to form, and eventually, at the very end, it has one piece and no holes. Now, doing this kind of thing, you get this incredibly rich signature of the shape of the object. And there are different ways to represent that. I'm showing something on the right called a persistence diagram. Doesn't really matter what it is. Again, this is a high-level talk. But it turns out that you can use this kind of analysis to figure out that a sunspot is about to go boom. So you can do this kind of what's called persistent homology analysis and get one of these complicated topological structures, signatures, like along the bottom of the slide. And the change in those signatures can tell you when the magnetic fields in what's called a solar active region are getting all tangled up to the point where they're going to reconnect and the thing is going to generate a solar flare. So topological data analysis is getting increasing use as a pre-processing technique for machine learning algorithms. So again, that might be something that's useful to some of you. Okay, I think we're moving close to the end, so I'll just, I'll talk about one more thing, which is kind of fun. The concept of topology came up back when we were talking about trajectories of dynamical systems. So TDA, topological data analysis, can be useful for studying those too. These two trajectories that I have pictures of here are actually different musical instruments playing the A below middle C. On the left is a clarinet. Okay, all right. Very long clarinet note, stop. And on the right is a viol playing the same note. Okay, so for us humans, it's not very challenging to tell a clarinet from a viol. Turns out to be really easy with topological data analysis as well. Now we could do this with, Fourier transforms or wavelet analysis as well, but nonlinear systems can have very complex frequency profiles, and this can help in some situations. Here's a more interesting comparison. Same note played by a grand piano.
Sorry to cut in. You might have to reshare. The sound's not playing.
Oh wow, okay. Let me take off my headphone. Maybe that will help.
Can you still hear me? Oops.
Yes.
Oh, okay, good. So this should be able to, let's go back to I'll just do this one. So, hello, wait, I'm in the wrong, there we go. All right, so there's a grand piano playing some note. It gets the A440. And here is an upright piano playing the same note. And they sound really similar, but again, from the standpoint of topological data analysis, you can really see the difference come out in the signature. And TDA can also be used in biological experiments. This is something we're doing with honeybees and the fact that the honeybees cluster at certain points in their behavior. And clusters are about pieces and wholes and things like that. So this has been a really nice application of that. And we're getting up to 1 p.m., so I'm not actually going to be able to tell you, unfortunately, about music and dance, but I will flash up one slide and tell you a little bit about what was going on here. So it turns out that there is a way to use the mathematics of chaos to generate musical variations. I'm not going to try. There's a way to do it. And so you feed a musical piece into this algorithm that basically fits it to wraps it around a chaotic attractor. And then you drop a new initial condition, run the trajectory around the attractor, and play the notes for the regions that it hits that you mapped onto it. It's a bad explanation. But it generates variations on music, kind of like a variation on a theme. This was Diana Davi's work. Wonderful idea. So one of my students did it for dance, and that led us down the primrose path of motion capture, and we ended up putting together, a performance piece in Boston and Boulder and Santa Fe that involved a duet between a human performer and 3 projected computer graphics avatars performing chaotic variations of a short phrase of dance. So that was also fun. One of the really nice advantages of this kind of work is it's a really great way to get undergraduates interested in STEM fields. It was a wonderful way to get my numerical computation students to actually be interested in things like splines for doing animation or doing solving ODEs. There's actually an application, a part of this application involves graph search. And so again, for people who are into computer science theory, you're teaching a theory or algorithms class. Getting kids interested in like Dijkstra's algorithm is a challenge, but if it's a matter of generating an interpolation for a human avatar, that's a good motivation. So these are the main collaborators on some of the projects I talked about in any kind of depth. There's faculty in pink, and postdocs in green, and PhD students in blue, and undergrads in black, and high schoolers in gray. And people move on. Tom and Josh Stewart are now full professors, which makes me feel old, and Mike and Jamie are in grad school, and Charlotte is actually a freshman in college. And there are many other people involved in the projects that I mentioned in passing. So many thanks to all of them for all their creativity, and thanks to you for listening. And we're past 1 o'clock, so I will stop talking. Should I unshare my slides so that I can see everybody?
Sure. Well, yes. Thank you so much, Professor Bradley. What a wonderful talk and wonderful examples. Thank you so much for sharing such relevant examples. I think each and every one of us can get something from that. Now we'd like to jump into and dive into our Q&A session. Just a reminder to our attendees online that to use the question icon, and don't be shy to upvote your favorite questions. So our first question that we have is, going back to your elbow example, Professor Bradley, why don't we need to know the acceleration to describe the elbow wrist system?
So, yeah, good question. So basically, if you have the position and the velocity, then you can derive the acceleration. So it's just, you know, mathematically, it's not any extra information. So just think about like doing a divided difference or something like that. But yeah, good question.
Thank you. Our next question is, could you comment on the stability of a Lorentz system and any other chaotic system?
Well, define stability. So if you think about the trajectory traveling on a chaotic attractor, in my field, we think about a dynamical landscape, and we think about the evolution of the system as kind of like a ball rolling around in a landscape. And you could imagine if there was a groove in the landscape and the ball were rolling around in the groove, kind of like, you know, those cat toys that have a ball and the ball runs around in a gutter, then it's very stable because the cross-sectional structure of the landscape will always gather the trajectory back towards, or any perturbation will get kind of damped back down. But if you're running along a ridge, then things aren't very stable. And I used the term Lyapunov exponent. That has to do with not just how fast things grow, but also do they grow or do they shrink? So the Lyapunov exponent will tell you if you're in this kind of part of a landscape or if you're in a groove. So are you running along a ridge or are you running in a groove? And we talk about what's called the transverse Lyapunov exponent. And you can imagine if you're a ball running around on a complicated landscape, there are going to be regions where the landscape around you goes down, and there's going to be regions where the landscape around you comes back towards you. So it's actually very complicated to talk about stability. The attractor will always be there, but how sensitive you are, the trajectory, are to perturbations depends on where you are on the attractor. So that's why my first answer was define stability. But the whole attractor is structurally stable. It's there.
Wonderful. Thank you. So we have another question actually from our in-person audience here. And the question is, since most systems are chaotic, could you talk about how long you can predict the dynamics of a chaotic system? Yep.
And that goes to that Lyapunov exponent thing, or Lyapunov exponent. I'm trying to pronounce it correctly in Russian. So if any small change will blow up exponentially, then what you need to do to think about predictability is to consider your initial uncertainty and then think about that uncertainty and how fast it's going to blow up and how certain you have to be about the prediction. I'm not sure if any of that made sense. So let's say you wanted to predict within an inch and you can measure within 1/10 of an inch. If you know the exponent, you know exactly how long it takes to take this initial 1/10 of a second, 1/10 of an inch uncertainty and have it blow up to the inch. So it's just a matter of dividing one by the other and taking e to the that and dividing by the Lyapunov exponent, and then you know the time. That was way too fast. I don't have a chalkboard, or it would be easier.
Thank you.
But it makes sense. I hope that, if if you know that the system magnifies small changes exponentially, e to the something t, and you have some figure of merit for how uncertain you have to be for your prediction to be right, and you have some metric for how uncertain you are at the beginning, then you can back out the t pretty easily.
Thank you. Another question from our in-person audience here is, can you describe how useful, in your opinion, digital twins will be in the future, and what kind of caution should be used when employing them?
Oh boy, do you have half an hour? Yes, a digital twin is a model. Models are only as good as their match to reality. I worry about digital twins a lot because, you know, if you have a complicated nonlinear situation and you don't get it perfectly right, this is following on the last question, if you're a little bit wrong, then the implications of that could be dire. And also the other thing that really kind of ties into this is the fact that we somehow, and I don't know why this happens, I have it too, I'm not just ranting about kids these days, but once you have a technological artifact, often you stop thinking and you just believe it. So somebody hands me a digital twin in a box and maybe I've bought it, I'm just going to believe what it does. And given how the issues involved in modeling dynamical systems, especially nonlinear ones, I worry about that a lot. And they're useful. Digital twins are great if they're good. If they're good.
Thank you for that perspective. We have time for one more question, and the question is, could you please share some examples where a combination of a closed form solution and a chaotic dynamics can help to capture the phenomenon better?
I don't know if anyone's thought about that, because that's kind of like combining, well, the old British expression chalk and cheese, which I've never understood why they combine it anyway. So a closed form solution and cannot coexist with chaotic behavior. So I'm not quite sure what the question is. Maybe the person could elaborate a little bit.
You know what, the question was anonymous, so perhaps that's good information if they can't coexist.
Yeah,
That might be the answer.
Can you read it again to me, please?
Sure. Can you share examples where a combination of closed form solution and chaotic dynamics can help to capture the phenomenon better?
Okay, interesting. So certainly if you are controlling a chaotic system with a traditional control theory approach, that's the traditional control theory does closed form stuff. So that might be the only example I can think of combining those two. In terms of understanding the phenomenon, I'm coming up with a blank. I can't think of a way that could be useful. So I apologize.
Oh, no apologies necessary. Just want to say my sincere thanks for you joining us today. It was a wonderful, wonderful presentation, and I'm sure many of our attendees enjoyed it immensely.
Great, my pleasure. Thanks for having me.
That concludes our session today. Thank you so much again to Professor Bradley for her remarks and her answers. And thank you to all of my ATCO colleagues and friends who helped put this all together. To everyone who has joined us today, just a reminder that to check out our social media feeds for information about past speaker series sessions, and also stay tuned for future announcements in 2023. In the meantime, please stay safe and enjoy the rest of your day. Thank you for joining us.